Hello everyone, this is our video example, the first video example related to our lecture on multiple reactions. In this case, we are looking at question 4.68 from the textbook, page 201. So go ahead and open that up, read that out first, and follow along as we attempt this question. So in this question, we have ethane that is chlorinated in the continuous reactor as shown below here. And some of the product that we want, our C2H5Cl, gets further chlorinated in an undesired side reaction to form C2H4Cl2. And in part B, it asks to take a basis of 100 moles of our product, C2H5Cl produced, assuming that the feed contains only ethane and chlorine, all of the chlorine is consumed, and we want to carry out degree of freedom analysis. In this case, you only ask for the atomic species. I'm going to go through all three methods of degree of freedom analysis to show that we're going to get a consistent value here. All right, so let's go ahead and do part B first. In part C, it gives us a yield, it gives us a conversion and a selectivity, and it asks us to find some of the unknowns that we are going to try to solve for. So let's do part B first. In part B, what we are required to do is to draw the diagram, label the diagram, and do a degree of freedom analysis. So single unit reactor with two reactions. We have a reactor, we have a feed coming in and a stream coming out of our for our products. We have our two reactions listed up there. Let's go through the problem line by line and translate any of the information we have into the diagram. We know we have a basis of 100 moles of C2H5Cl produced, so that's on stream 1. So number of moles of C2H5Cl in stream 1 is 100 moles, that's our basis. And it turns out that that's the only piece of information that's given to us in part B. The other thing that we know is that the feed contains only ethane and chlorine. So we can label our ethane and chlorine in terms of the actual number of moles. So number of moles of ethane, number of moles of chlorine in the feed. Now we need to decide what is coming out of the reactor in stream 1. We know that all the chlorine is assumed to be consumed, that's given in the question, so we know that we have no chlorine coming out. We're going to assume that not all the ethane is being consumed, so we have ethane that's going to come out. At the same time, we're going to have all the products that is occurring in this reactor coming out. So what are the products? We have C2H5Cl, that one is already labeled. We have HCl, we need to label that, and we have our C2H4Cl2. So we should have three products and then our ethane. And so now the three that have not been labeled is our C2H6 that's not been reacted, our HCl, which is one of our products, C2H4Cl2, which is the other product we haven't labeled. So that's our fully labeled diagram. Let's circle all our unknowns. We have 5 unknowns in here. Let's go ahead and do our degree of freedom analysis. I'm going to do all 3 different methods, even though the question is only asking for atomic species. Here's our diagram again. Let's look at the molecular species degree of freedom. First thing we look at, number of unknowns. We have 5 unknowns that's circled up in the diagram there. Next thing to do is to add the number of reactions. In this case, we have 2 reactions. The next thing is to count the number of molecular species. In this case, we have 5 different molecular species. We have C2H6Cl2, which is coming in, and we have the 3 products, C2H5Cl, HCl, and C2H4Cl2. So we have 5 different molecular species. We can write 5 different balances. We end up with a degree of freedom of 2, which means that we cannot actually solve this question completely. So let's double check this with our atomic species degree of freedom. In terms of atomic species, we have the same 5 unknowns. We don't add any reaction. In terms of the number of atomic species that is reactive, we have 3. We have carbon, hydrogen, and chlorine. And that's all we have. We end up with a degree of freedom of 2. If you go through the extent of reaction degree of freedom, it is actually the exact same as the molecular species, because in this case, all the 5 molecular species that we listed out down here in the molecular species method are reactive. There's no non-reactive species. We don't have to split that out at all. So it's going to look exactly the same. What does a degree of freedom of 2 means? It means, number 1, we cannot solve this problem fully. We cannot solve for all these 5 unknowns just based on the information given to us. How much more information do we need? We need 2 more pieces of information. And those 2 pieces of information are given in part C. In part C, we are given 2 process specifications. The first one is the fractional conversion of our C2H6. Second one is the selectivity of our desired product to our undesired C2H4Cl2. So with these 2 process specifications, our degree of freedom should drop to 0. And this will allow us to solve for all 5 of our unknowns using either the atomic or the extent of reaction method, which we will go on to do after this. But before we do that, one of the difficulties is really translating our process specifications that are given in words, that's listed up here, into an equation form, casting it in terms of the variables we have listed on the diagram. So what I want you to do is go ahead and pause this video, write out these two process specifications in terms of equation form with the variables that we have listed on this diagram. Once you're done, replay the video and you can double check your answers. All right, welcome back. Hopefully you have a chance to try writing out these process specifications. In terms of the fractional conversion, we have 15% converted, which means 1 minus 0.15 is left. So 85% is coming out. 85% of what went in, which is our feed, is going to come out in our stream 1. So that is our fractional conversion of C2H6. In terms of our selectivity in general is one of the easiest specifications to write. It's just the ratio of your desired to your undesired product. So it's just the number of moles of C2H5Cl to the number of moles of C2H4Cl2 in our product stream, and that's equals to 14. So with these two process specifications coupled with the balances that we have written in our degree of freedom, we should be able to solve for all our unknowns. I'm going to do the atomic and the extent of reaction method now. Let's start with the atomic species degree of freedom. Here's our degree of freedom that we had before, but remember we are going to subtract another 2 specifications, and that will give us a degree of freedom of 0. So we're going to solve for our 5 unknowns by using our 2 specifications and our 3 reactive atomic species balances. First one, I'm going to start with selectivity. If you look at the selectivity spec, we actually only have 1 unknown in there, which is the number of moles of our undesired product, because we have to pick the basis of 100 moles of desired product. So from here, we can calculate the number of moles of undesired product, and it's 7.14 moles. Like I said, in general, what I like to do is look at the specifications first because they're generally easier and most likely to be able to solve for right away. Let's look at our second specification of fractional conversion. It is relating the moles of ethane coming in and the moles of ethane coming out. It turns out in this case, both of them are still unknowns, which means we need to couple this. Either look for another equation that we can solve for something right away first and then come back to this, or in some cases, and in this case, look for another equation that involves the same 2 unknowns only and then solve these 2 equations simultaneously. So how do you decide which one would it be? We have our carbon balance, hydrogen balance, or chlorine balance. If you look through the process here, what are the unknowns we have left? We have these 2 on the feed stream and then these 2 on our product stream. The 2 unknowns that we want in an equation is the C2H6, so this one and this one, which means we don't want our chlorine to appear anywhere or our hydrochloric acid to appear anywhere. So it turns out that you'll realize that the carbon balance will not involve these 2 unknowns at all. By writing the carbon balance, what you're going to see is you're going to be able to have these 2 unknowns in that equation as well. So by writing the carbon balance, in is equals to out, we have carbon coming in C2H6, carbon coming out in 3 things, our C2H6 and our 2 different products, the wanted and unwanted products, which we already know. So now we can simplify it and you can see that we have the exact same 2 unknowns. 2 equations, 2 unknowns, we solve them simultaneously and we end up with solving the 2 unknowns. I'm not going through the math here. I will be posting the actual solutions with the full math of step-by-step how do you substitute and solve these 2 simultaneously. So if you are having problems with the math, go ahead and look at that solution that's posted online. All right, so now we have our carbon balance. We are left with 2. We are left with our chlorine balance and our hydrogen balance. If we do a chlorine balance, you'll see that you'll involve our last 2 unknowns because we have Cl2 and HCl. So the more obvious one to do next is our hydrogen balance. So here's our hydrogen balance. There are many different terms in there. Go through each term and make sure you understand where the coefficients come from and why there are the terms in there. But in this case, the only unknown we have left is the number of moles of HCl. Yep, I circled that. And here we go. The number of moles of HCl is 114.6 moles. With that, we have our last balance to do, our chlorine balance. Writing out the chlorine balance, we have 1 unknown left, which is our chlorine in the feed. From there, we can calculate as 104.5 moles. So we have completed solving this problem. Before we move on to the extent of reaction, remember to go back to the question and answer the question. The question asked for the feed ratio, so chlorine to C2H6. We already have the values. Number of moles of chlorine fed in is 114.5. Number of moles of C2H6 fed in is 714.3. So we have a feed ratio of 0.16. The next thing it asks for is the yield of C2H5Cl. The definition of yield of our product is the number of moles that we get out over ideally how many moles that we can get out. So we're going to cast our yield in terms of our C2H6. So the ideal number of moles of C2H5Cl is if all the C2H6 we put in are converted to our desired product and that we do not have this undesired side reaction. So once we form the product, it does not go on to participate in this second reaction that's going to consume some of that away. So all the C2H6 fat reacts to form only our product, and the unwanted side reaction, we consume some of this product, does not occur. Given these two assumptions, ideally how many moles of C2H5Cl are we going to get? It is a 1-to-1 ratio compared between our product and our C2H6. So it is just equals to the number of moles of C2H6 that we fed in. We already have those numbers. We can put that into here. So the yield of our C2H5Cl is 14%. All right, so now let's move on to the extent of reaction method. In the extent of reaction method down here, from before, the selectivity specification is going to be the same like we did before in the atomic species, so I'm not going to repeat it here. I just repeat the solution that we got, 7.14 moles. Now we're going to have to solve for our remaining 4 unknowns, and we already saw that the second specification contains 2 unknowns and we can't solve it right away. So let's write out all extent of reaction equations together with the specification and then start to outline the strategy of where to go next with those equations. Here are all our 5 reactive molecular species extent of reaction equations. Go through each one of them and make sure that you understand each equation. Remember here in this case we have to solve for 2 additional unknowns, XC1 and XC2, which are our 2 reaction unknowns that are in our degree of freedom right here. So looking through this set of equations, you realize that in 5, which is our undesired product, we can solve for our XC2 right away. That's all we have there. Once we have that, we can put that back into equation 3, which is our desired product extent of reaction equation. That gives us our XC1. With XC1 and XC2, you can put it into the chlorine and the hydrochloric acid balances, the extent of reaction equations, and you can find the number of moles that are coming out right away. Now you realize that we still have a specification we haven't used. What you realize that is in equation 1, you have the 2 unknowns of our C2H6 coming in and coming out. Once we know our XC1, which we know from above, we are going to solve 1 and 6 simultaneously. So again, we have the same 2 unknowns in 1 and 6. We're going to solve them simultaneously, and you're going to end up with the same answer as we got in the atomic. All right, so what you realize is that the way I've been presenting these equations are in a very systematic manner. I'll solve this first and you'll get to the next one that will allow me to solve another one. As you're practicing these problems, it might not be obvious to you. So go ahead and get more practice with this. If you are stuck and you don't know which equation to write, just write out all the equations that you know are available. Circle all your unknowns in those equations and then look through them, something like what we did here in the extent of reaction. So don't worry about trying to process it through without writing out the equations. If you need to, write out all the equations and then from there strategize the best way to solve these set of equations that you have. So that's all we have for this example. I'll have one more example where we'll actually just set up the problem and I'll post the solutions in terms of the math. Work hard, be smart. I'll see you next time.